got this yet. Okay, so just look at all this. Okay, I will share the links to you. Okay, and you can have a look on this. Okay, so that is for the library plagiarism information page. So the other one, this is more on the promotional. So we will go to this one. Right? Some of you may know that I'm actually the Utah X-ray student branch advisor. Right, so I will do some promotion here. So X-ray Utah student branch is going to do the recruitment drive on 29 June to 3rd July in this week. Right. So for those who are interested on air conditioning, heating, ventilating, and air conditioning, including the refrigeration. So you, this is one of the most relevant society you can join, right? Utah X-ray student branch. So if when you join, I hope that you try to be active so you can get the most benefit out of that. Okay. So if you look at that, we have some previous sharing session. This one cancer is due to MCO. Second. Alright, so if you look at the sharing session here, this is 4 people there. So 3 out of the 4 is actually your seniors. Your Kosen is chemical. You can see now he's regional product managers from Daikin. Keith Law is your very senior in Utah. I think he graduated in 2011 or 12. So now he's a director. He owns his own consulting firm. So Rex is I think just graduated 2 to 3 years, but now he moved to Singapore. Right? So these are the examples you can learn from them. Right? If you are interested on this, we call it HVAC and R industries, or even we call it construction M&E industries. Okay, so that is for advertisement purpose. So now we will move to our lectures now. Continue our lectures. Let me see. So for the X-ray one, I also share the link. So if you are interested. Okay, so now I will turn off my videos, then we'll go for the lectures. So how many we have now? 1, 2, 2. Okay. So let's start our video recording. And then, okay, then we'll move to our screen 2. Okay. Alright, so we'll move on. I think last week, one of you actually asked maybe to look into what is a full join and half join in more detail. maybe we can look at this example actually. Okay, so let's see. Okay, so we for example, now we look at this diagram. Yeah? So we have so many linkage there, right? So again, you'll find out that the ground link is considered one of the links. Right? So because if you look at that, this part, this part, this part, and this part, their dimension or is fixed, right, between them. So that's why we can actually consider this is one of the link. So we call it link 1. Then we have link 2, right, link 3, 4, where is the one? 5, 6, 7, 8. So 8 is a sliding slider, right? So this is what we call link. So if we calculate it, that's why we get the 8 link there. So now we look at the join. Okay. So when we say join, there is a full join and half join. Okay. So there is a full join and a half join here. So full join basically it means that you only have 1 degree of freedom on the join. In another way of saying it. So if you look at here, this one, the link 2 here, link 2 and the link 1 or the ground there, you can only attach with the pin. So you can only have one rotation motion. So you can't have any translation motion and so on. Right? So and also you have to remember that we are now on the 2-dimensional problems, not 3-dimensional. So it means that this one lay on this screen or this paper, so it can only rotate on the axis coming out from the screen. So X and Y is fixed because this is a pin joint, so that's why we have 1. So any other pin joint, so we have the 2 here, okay, 3, 4, 5, 6, 7, 8. Right? So 8 pin joint, as what you can see here. But the problems that we are having now is this at this one, at this point here, at the center here, there is a two, or we call it 3 link together. So if I fix one link, means that the other 2 links will move freely. Yeah. So that's why instead of we say this is 1 full join, then it becomes 2, right? We have 2 there. So there is another one is on this sliding. So if you look at the slider here, right? Because this is a slider. So what you can do is you can only slide on this direction. So that's why you only have 1 degree of freedom system. So that's why the sliding is considered a full join here. So 8, we have 8 here. Then this one we add 1 more, 9, right? And then the sliding is the 10, right? So that's why we get the join, 10 join there, right? So there is no half join, right? We will look at the half join on the diagram next to it, right? So you just substitute all these to the equations we have. So for example, this one you substitute this is the 8 link, and then this is a 10 join, this is 0. So we will get 21 minus 20 minus 0. So you will get this. Sorry, it should be 1. So we will get 1 degree of freedom system. Okay. So that is on diagram A. Yeah? So now if we move on to this diagram B, so again you will look at that, the ground here is considered 1 link, right? Because the measurement from here to here, okay, and to here, they are all fixed. So we have ground as one of the link. So 1, then 2, 3, 4, 5, 6. So we have 6 links there. Okay. Then we find the pin joint. Okay. So we have 1, 2, okay, 3, 4. This one is multiple. Okay. You can see if I fix this, then I can move this one and this one. So instead of we calculate this as a one full joint, we say this is a two full joint. Okay. So now we have 1, 2, 3, 4, 5, 6, 7. So we have 7 full joint. Okay. So now there is a contact here. Okay. So if you see the things that we have here now for this part. Okay. So it's different from the slider that we have on the left, because this slider, if you look at it, is only doing sliding. But for this link, the link tree on this diagram, so it can actually rotate. Right? It can rotate on this surface, but then this contact can also move horizontally. So that's why we call this half joint. Yeah? So half joint, how we mention that is just a second. So we have one half joint. Yeah? Okay, so then if we move back to look at this, so let's see what we have. So we have 6 links, 7 full joint, and 1 half joint. Yeah? So what we get here is this is 15, this is 14, this is 1. So end up we get 0. So what does it mean with 0? Mean that if you set up this linkage, right, in this way, basically you can't move it. So it become a rigid part. Right? There is no motion you can do. You cannot, when you push here, it will not move. Right? Or even you push here, it will not move. Right? That's why your degree of freedom is 0. But for this one, you just need one movement to define the rest of the movement of the linkage. So we read the sentence at the bottom there. We will now define a crank as a link that makes a complete revolution and is pivoted to the ground. A rocker is a link that has oscillatory back and forth rotation and is pivoted to ground. And a coupler or the connecting rod is a link that has complex motion and is not pivoted to the ground. So ground is defined as any link or link that are fixed, non-moving, with respect to the reference frame. Not that the reference frame may in fact itself be in motion. So what it means here is this ground, even though now we say it is a ground, so there is a possibility is moving ground. Maybe just to show you this. Okay. So for example, this is the engine. Okay. So as I mentioned before, the red color one will treat it as a ground. Then there will be a 4-bar slider linkage. So we have a crank, a connecting rod, and a piston. So this is all. So the red color one here, we consider link 1, and then crank link 2, connecting rod link 3, and the piston is link 4. So when we turn, okay, remove the piston, you will see that actually relatively the red color one is not moving. That's why we consider that as a ground. But if you imagine that if this engine is put on the motorcycle, basically then this engine is also doing some motion, right? But now we look at the relative motions, so that's why we will fix this. Okay? because now how the engine move is not our concern, right? When we study mechanics of machine on this engine, so basically the movement of this linkage inside the engine is our concern, right? So that's why we can take the engine itself as a fixed part, right, or non-moving part. Okay, so we come back to here. So I hope now you have slightly clearer. So what is the half joint? Okay, what is half joint and what is full joint? Yeah, okay, full joint. Okay, so normally this will be confusing the sliding one. So you have to make sure that if it's just doing sliding, then it's a full joint. Right? But when it can slide and rotate, then so the other thing you have to be careful is on the multiple joint here, right? So depending on how many link is attached to one pin, right? So how you can calculate it is always if when you come to the joint, for example this one, so then you can fix one of the link and see how many movement you can have, right? Then you can count the number of joint. Okay. Okay, at the beginning of the chat, there I share a YouTube video, so it actually describes to you the Grashof law. So this is applied to basically a 4-bar linkages, okay? So you can watch the video. As we tried it last week already, when I show you the YouTube video is not really working through the Microsoft Teams. So you can watch it on your own. It's just a 9 minutes fast video. So this is a Grashof called it a linkage, or the Grashof law. So we can have a 4-bar linkage. So again, this is a fixed ground. Alright, so there is a link 1. So you can see they never mentioned, but we can write it down, link 1 here. So we have 2, 3, and 4. So now, if you imagine that now I turn this, okay, I rotate this, so I will move this point to this direction, this point to this direction. So what happened here is then this, that's why this one we call it rocker. So it's only doing rocking, right? So this one we call it the link 2. Normally we call it crank. And this one we call it connecting rod. Okay. So if my crank now rotate, then this one, the link 4 will doing the rocking. So that's why you call it crank rocker. Okay. So we can have another setup, which is same as the piston that I show you, the engine I show you. So they call it slider crank linkage. So now again the ground is a link 1, so link 2 is the crank. So if you rotate it, you'll find out that your slider blocks will move forward and backward. Okay, on that. So the link 3 here is a connecting rod. So we're connecting the end of link 2 to the piston. Okay. So the next one is, if you look at that, we have this special profile here. But if we at one moment, at any or at a single moment, we can actually fix it, and then we can draw the linkages as well. Okay? Because if you see here, there is a groove here, and then this pin will move along the groove when the link crank 2 is rotating. Right? So if I freeze it at this position, now I can say that my ground is a link 1, okay, and then this is my link 2. So I just take the measurement from this point to the center of the bar there, so I can connect, and then this will form what we call an effective link tree, right? So not this direction, right? It's the red color one, is the effective link, because that is the place where you actually contribute to the kinematics calculation. And then there is a sliding, so we can call that as a sliders 4. Okay. So similarly, also we can have a straight groove here. Okay. So again, when we freeze this position, okay, so we can actually find the link 2, link 3, and the sliders for this motion. So this one they call it Scotch Europe. Basically, you can find it in because what the baby cot. If you have baby cot in your house or in your relative house, right? You can open up and then you find out that what they do is they just put on motors, right? Put the motors on here. That's why you can change the motor speeds, and then you can make this movement. You can change the speed of this movement, right? So the next one is inversion and Grashof conditions. Okay. So for example, we have this 4-bar linkage. Right. So we have link 1 basically is again the ground. Then link 2 is this crank. Okay. Link 3 is connecting rod. Right. So sometimes you will see in the textbook they write CR, which is a connecting rod. And then link 4 is a slider. Okay. So what happened here is when we fix different link, then the motion will look different. So for example, now for A, we actually fix link 1. So what will happen is we try to move the link 2, so it will form a rotation because we fix this. Right? We fix this point over here, so it will link 2 will form a rotation. Okay? So when link 2 forms a rotation, then it will pull the slider 4 up and down. Right? So there is what will go on. So but when we move to B, what happened here is now we fix the link 2. So this one don't move. So what happened? If you try to slide the slider up and down, it will not just do up and down, it will actually doing this. Okay. Okay. Means that once I pull down here, so this one it will form this way. So basically your linkage will go like that. Okay. So if I pull it up, so your linkage will go there. Okay. So that's why it will do swing on this line. Okay. I don't draw exactly at this point, but I stay here. Okay. So for the C, so what happens if I fix the link 3? Okay. So then again, my link 2 will do a rotation. Okay. When you do rotations, then what happens now is this bar will go up and down, and also it will rotate. Right. The bar will rotate on that point. This point. Right. Because you can try to plot it. So for example, now I move to this point. So for example, I try to move to this point, so I have this link here. So what happened here is now, I will get that there. Okay, so your sliders will actually rotate into this direction. Okay. and so on. So now we can look at the last one here, D. So now what happens if I fix the slider here? Okay, when I fix the slider here, so what you do is the link tree now will rotate based on the P there. Okay, so this is what with the same link. So if we set different boundary condition to it, so we will get different motion. Okay, so now we look at the Grashof condition. It's a relationship that predicts the rotation behavior of rotation of a 4-bar linkage. Okay, so before we start to look into the linkage, so few things or few terminology you have to know. So we have S is the shortest link, L is the longest link, right? And then P and Q is some of the other two links. Okay, so in the video we also explain on this. So now if we look at the case 1, okay, what happened here is the shortest link plus the longest link is less than the other two links. Right? So if you look at here, where is our shortest link for diagram 1? So this is the shortest link. This is the longest link. So for this is the P and Q. Okay. So mean the SL, S plus L is less than the P plus Q. So what happened here is you will see that you can do this rotation. Right? Same as here, this link now you can also do the rotation. So we call it crank rocker link. Right? So we have this crank where you can do the rotation, and then the rocker which do the back and forth at the specific angles. So what happened to the double crank? Right? So what here it means that now this link can do a rotation in this way, and then this one can also do another movement. Right? So then we also have a double rocker. So now what happened here is these two bars cannot move for full rotation because of the dimension issue. Right? So but the two of them will be doing the double rocking. So the second case here is when our S plus L is greater than P plus Q, right? So we can have a triple rockers here. So as shown in the diagrams, right? So case 3 is when it's equal. So we have 3 conditions, right? So we can have this parallelogram form, anti-parallelogram form, and also the deltoid or the kite form. So this is classified as a special case of Grashof linkage. Here we never mentioned, because case 2 basically we call it non-Grashof condition. Okay. Okay. I think for those who attended the tutorial, maybe Prof. Andy already touched on this graphical linkage synthesis. So what it means here is actually when we want to design the linkages, we can use it. Sometimes it's easier to use a graphical linkage synthesis method. Mean we can draw it out, right, using your compass and so on. So we'll look at the functions, path, and the motion generation. So function describe the mathematical formulas. Then path defined as a point in the plan such that it follows some prescribed path. Because why we need the linkage is basically we want the linkage to do certain movement. Right? So for example, in your car you have the tank valve. So you want the valve, how the valve is opening and so on. So that's why we will design the path of the movement. Right? Then the motion defined as a line in the plan such that it assumes some prescribed set of sequential position. So the limitation condition, so we have two critical position here. One is the toggle position. So this is a lock position where two of the moving links form a collinear configurations. The other one is what we call a stationary point, right? So when the shortest link crank is collinear with the coupling, right? So we have this so-called stationary point, right? Basically, I think the stationary point you can also experience, right? With when you are cycling, right? So if you try to do a cycling, you will find out at certain position you will not be able to move the pedal, right? Means that is a lock position that you can't move your pedal. That's why then you have to move your pedal to another angle and then start your cycling, right? So this is what happened, right? So now we look at this what we call it the toggle positions, right? So toggle position means that when two of your link form collinear. So for example here, we have, maybe I have to use different colors. Let's see. So we have link 2. Okay. Link 2 is here. Then link 3. And then link 4. So now you can see your 3 and 4 form a collinear position. So same thing is happen here if I go the opposite direction. So this is link 2, link 3, and link 4. So again, your 3 and 4 form what we call it the collinear position. So you can also see that the application here, sometimes we purposely do it. So this is the bottom one, there is a truck body. So we have a truck tailgate here, right? So what you do is sometimes we want it to hold it very firmly. So that's why you purposely design this two link. When you open up, this two link is at the collinear condition, position. So what you have to do is, now the problem is when you want to lift it up, it's locked, right? You can't lift. So normally what you have to do is you have to bend it a bit, right? To change its position, then only you can start to lift it up from that position. So this is one of the application of why we need to know this. All right. Yes. Anything? No. Okay. So the other one is stationary position. So maybe we go back. So we it defined that when the shortest link crank is collinear with the coupler, right? So means that here, if this is my crank, right? Just back to the you see, it say the crank is collinear with the coupler or connecting rod, right? So this is a crank, which is a link 2, and then I draw in another color, yeah? So this is actually your link 3. So they are collinear. The link 2 and link 3 are collinear. They are on the same line. So this actually form the stationary configuration. So the other position is over here. This is a crank. And this is the coupler or connecting rod. So they form a collinear position. Right? So there is also we call it a stationary position. Okay. So another information we have to know is what we call it the transmission angle. Right? So this is the angle between the output link and the coupler. So remember that the output link and the coupler. So normally link 4 or the rocker arm is considered the output link. The reason behind is normally what happened here, for example, the linkage here, we will always put the motors here. So this motor will be served as a drive. That's why on link 4 is considered output link. This is a normal condition. Now you can have the other way around, but most of the application will be in this kind of configuration. So that's why when we say output link is normally referring to the link 4. Alright. So and then this is link 3 is a coupler, or sometimes we can call it a connecting rod. So what you do is basically you will find this opening angle. So we call it mu, which is your transmission angle. But you have to know that the transmission angle is varies continuously. Yeah, right. When we start to turn to the next position, you'll find out this will have another new angle here. Right. So that's why the complex of dynamics or even in mechanics of machine and so on, the difficult part for you to study is you have to be very clear that whenever you do calculation, you have to freeze the motion, right? Where you want to freeze the motion, right? Which part is your interest, right? That's why on these subjects, I will not be asking you to calculate what is the torque you get from at this point, yeah, for all the position. Because if you want to calculate the torque that you receive at this point at all the positions, so you have to calculate maybe every angle you change, right? Because every angle you have, the torque is different, right? You can only do it using maybe Excel or using a software, right? But doing manual calculation will be quite difficult, right? So later you will see this F3, 4, and so on in the next topic when we zoom into the linkages. So you see that there will be a T2. So normally this is supplied by the models, and then this is a receiving port from your linkages. Okay, so now we move into the position synthesis. Means that now we can define what is our output position. Then we start to design our linkage. So this is a simple rocker output with 2 positions with the angular displacement function generation. So we will design a 4-bar Grashof crank rocker to give a 45 degree of a rocker rotation. So what it means here is rocker position, so we need 45 degrees. So with equal time forward and backward. So from a constant speed motor input. Right? So what it means here is, first we will define these two positions by setting this angle 45. Okay. So the next thing you have to do is then you have to define the length of this link. Okay. This one you set. Okay. How far you want to go. Okay. So normally you can set how much this distance you want to travel. Right? That's why when you have this distance, so basically then you can draw a line across the 2 points here, this point and this point. You draw a line through, and then at any location, you can form this. Right? You can form it here, O2. You can form it further over here is fine. Right? So this one normally the limitation is on the space. Right? Depending on how long your linkage can have. But in the industry, normally people want as smaller as possible. Okay. So once you let me erase this one first. So for example, now we fix it this point. This is also defined by you as a O2, right? By having this line, right? So how to define the crank, right? So this crank length will be actually half of the distance here, right? Because if you imagine this one, when you turn all the way to here, this movement will form the D, alright? So that is how we do the two position synthesis. So we have to define what is the output we want, then the length of the link for. So you can, the other way is you can set, because once you fix the link for, you can draw this line. Then we just cross a line through. Then you define where you want to put your O2. Once you know your O2, then you can define where is your pin for your crank tool. Right? So that's why then you start to have your crank tool. This is your crank tool or the link tool, and then you can connect. Right? This one, sure, you connect to B1, you don't connect to B2. Because you connect to B2, then it can't move. There is a minimum position already. Right? So you will connect to your B1, and that is your link tree. And then, which color? And then this will be your link 4. Right? So this is how you build your 4-bar linkage. And if you really want to show it, then this point to this point will be your link 1. Right? So this is how you get your 4-bar linkages with these two predefined positions with the angle of whatever angle you want. Okay? But when we have this kind of rocker mechanism, right? Normally, or we call it rule of thumb, the maximum angle that we normally fix is 120 degrees. If you more than that, you have a lot of issue on the smooth movement, right? So you can look at this, or you can also see this in all the hydraulic machinery design, like the excavator and so on. They also have similar one, right? But for this part, they may not use motor. They are using the piston, right? To also do the same thing. This two position movement, right? So this is how we construct, right? So set the angle, right? And then choose the length, right? You have to choose the length of this. Then you start to draw this line, right? Then how you find the length of the link tool? You can use your compass, right, to draw this line. So maybe you put the color. So for example, now you put your compass here, then you start to draw this line and this line. So then you put another point we got a point B here, we draw another line, this one and this one. So from here, what you do is you break this horizontal line here into two. So that's why you get this distance that can be transferred back to as your crank length. Okay. So again, this is your choice of length where you go. As I mentioned, this is governed by the space available right, in your design. Okay. So this is a method, a stated, so you can follow. Right? So we draw the output link O4B in both extreme position, which is 45 degrees apart, right? The angle. And then we draw the code B1, B2 and extend it in the either direction. Then we can define where is our O2, then along the B1, B2 line. And then we do the bisect line, right? And draw a circle of that radius about the O2. Then label the two intersections of circle and B1, B2 extended, A1 and A2. So then we can measure the length of the coupler. So and also measure the ground length 1, crank length 2, and the rocker length 4. So then we can also check if whether is fulfill the Grashof condition, or which is the case to fall under. Okay. So if we found this is a known Grashof condition, so we can redo the step 3 to step 8 with O2 further from O4. Okay. So means we increase the length of it. Okay. So make the model of the linkage and check its function and transmission angles. Okay. So actually, if you buy the textbooks, there is a program called Linkages. So you can try this using their programs. Okay. So the other one is two position with complex displacement now. Okay. So just now is a movement between the 2 points. Right? Now it's a movement for a link. Okay. So for example, here now I have originally I have this C1 D1. I want to move the C1 D1 to C2 D2. Sorry. So how can we do it? Okay. I think the next slide. Okay. So this is how we do it. So we have C1 D1. Then we want to move it to C2 D2. So what you do is, okay. Or maybe we go through the description first. So we draw the link CD in its two desired position. So we have CD1 and C1 D1 and C2 D2. And then draw a construction line of point C1 to C2 and D1 to D2. Then bisect the C1, C2 and D1, D2. Extend their perpendicular bisector to find the O4. Right? Then select a convenient radius and draw the arc about the rotor pool to intersect both line O4C1 and O4C2. Then label the intersection B1 and B2. Do the step 2 to 8, okay? And then complete the example 1. And then because after we complete this up to this part, so the bottom here will back to the 2-point position that we have on the example 3.1. So that's why we can repeat this on the example 3.1, the method. Okay, so what it is you connect this. Okay, so the next step is reconnecting this C1, C2, and D1, D2. Okay. So what you do is that after this, you between the C1 and C2, you find this line, which is 90 degrees. Also D1, D2, D1, D2, you find the center line here. Okay, 90 degrees. So how you find it? You are actually using this drawing. I hope you still remember how you can find the center line using your, do we call it protectors or compass? Compass, right? You can use your compass to draw this. Okay? So then you can form this rotor pool here. Right? From this rotor pool, then you can connect this to C1 and C2. So means that now if this green color one move from C1 to C2, I will form this motion. Right? So after this, that's where then we follow the example 3.1. Then you have to find where you want to draw a line across. So in this case, you draw it here B1, B2. Right? Then it will. Then if you zoom in here, it will similar to the example 1. Okay, where you want it to go. Right? Oh, you never draw that. So you can refer back to what we have here, the example 3.1. So means you draw your O2 and then your crank. Right? This is your link 2, and then you draw your link 3, for example, over here. Right? So this is another one, coupler output. Just now is a rocker output. Right? If you look back on here, this is a crank, this is a coupler. So basically this is a rocker. So we call it rocker output, meaning the output is at the rocker. So what happens if I want the output is on the coupler? So the equation given is still the same. From we have C1, D1, right? Now we want it to move to C2, D2, right? But now the thing is this must be link 3. So what we can do? So this is the method we can use. So we can draw the link CD in its 2 desired position. So then draw a construction line from a point C1 to C2 and D1 to D2, bisect again the C1 and C2, D1 and D2, and then we extend the perpendicular bisector in the convenient direction. The rotor pool will not be used in this solution, so it's slightly different from the rocker output. So select any convenient point on each bisector. There's the fixed pivot O2 and O4 respectively. Then connect the O2 with the C1 and call it link 2, and then O4 to D1 and call it the link 4. So line C1 D1 is link 3, line O2 O4 is link 4. So later you have to look at this. Then we can again check the Grashof conditions. Right? So if not specified, then we can repeat the steps. Right? But the problem now is basically any Grashof condition is acceptable depending on your application. And then construct the model and check if the function, to be sure it can get the initial to final position without encountering any toggle position, any limit. Right? Then we can also check the transmission angle. So what we have here is we have first draw the C1 D1 and then C2 D2. So what happened here is we can now we can then draw this line and then find its perpendicular. Right? So the other one is over here. Finding is perpendicular. So just now we will take this point, right? If we need a rocker output, but for this case we will not take this because we are not working on the rocker output. So what we need, what we will have to do is, for example, now on the C1 to C2 we have this line. So at any point you can set the O2 here, you can set the O2 here, you can set O2 further. It's up to the space available again. Okay. So for example, now he set the O2 here. That's why then you can build your linkage. So I draw this one. So this is your link 2. Okay. And then now it's not C1. Now the link 3 is C1 to D1 is your link 3. So again, then where is your O4? So you can find any point along this line. Right? So in this case, it's set it here. You can set it further or shorter. But as I mentioned, normally we don't want the rocker angle to be too large. So you can set it further if you want. Right? So in this case, it's set it here at O4. That's why then this one will be your link 4. Okay? So this is your link. Okay? The 4-bar link. So your link 1 is the distance between the O2 and O4. So how your geometry want to look like is up to the designer. So if you want a very simple one, then your link can be just a simple road. So if not, then you can draw maybe something like this. Instead of a straight line, you use a curvature linkage. Okay. So for example here you see you use the straight link. Okay. But for D1 to D4 here, or the link 4 here, we use some curvature. Okay. This outlook doesn't affect our calculation. Okay. For kinematic analysis. Okay, the next one is the 3 position. Just now we only do 2. Now what happens if we want to fulfill the 3 different positions? So which are the 3? So we have C1, D1, this is the first position. And this is the second position. And then we have the third position here. So how we want the link to move in according to these 3 positions? So this is the method described. So again, we draw the link, right, all the 3 desired positions, and then construct a line from C1 to C2, C2 to C3. Then we bisect the C1 and C2, C2 and C3, and then we find the intersect there, so we can label it as O2. So we'll repeat the same step to D1 and D2 and D3. So again, the intersection that we found will become our O4, right? Or the rotation point of our link 4. So then we can connect O2 to C1, which will form the link 2, and then O4 to D1, which form the link 4. Okay? So again, then what is the remaining is the C1, D1 will automatically become our link 3. O2 and O4, the distance, will become our link 1. Okay? So again, you can check on the Grashof condition. Okay? So again, here it mentioned that any Grashof condition is potentially acceptable in this case, because our movement is on the coupler, right? So then we can again find to check, try to avoid any toggle position. As I mentioned, once you fall on the toggle position, basically you lost all your movement, right? Okay, so now just now what he mentioned here is C1 to C2. You draw a line, then you cross it, okay, with a 90 degrees here. Then C2 to C3, you draw the line, cross it, the center line. Yeah? So these intersections will form our O2. So same thing, go to the D1 and D2. You draw the line. So normally when I draw this line long enough, okay, because we do not know whether the intersection will be on the top or the bottom. Okay, so you can draw long enough. Then we will have to draw another line, D2 to D3, and then you find the intersect. So this line can always use the compass, right? You just draw like that. Okay. Fix this point, draw this line, and this line with the same radius, and then fix at the D3, draw this line, and this line with the same radius. Then you just join these 2 points. Okay. So you draw long enough, then you find out that this is the intersect. So that will become our O4. So how then we will actually try to construct the linkage, right? Because as I mentioned, the C1, D1 will be our coupler, right? So they will form a link tree there. So link 2 will be from here, O2 to C1, right? Link 3 is C1 to D1. Then link 4 is D1 to O4, right? So there is link 4. So basically, for example, now the same link, when you move from C1 to C2, so now your new linkage will look like this. Maybe I clear it off first.
Sir, we can't hear you.
Since when you can't hear me, just listening. That's about. Since when, which slide?
The previous slide.
This one. Am I right?
Yes, yes.
I didn't notice that my mic is mute. Okay. So what I mentioned here is we can I just want to show you how our link look like. So just now you mentioned that when we can connect O2 to C1 to form our link 2, C1 to D1 to form our link 3, D1 to D4 to form our link 4. This is the first position we have. Okay. So if I start to move my link 2, right, move from here to here, that's why then the linkage will look like the red color one we have here, right? So I can further move it to the final position here, so it will form the yellow color linkage. So when my link 2 move back and forth this way, so my coupler will always move from here to here and then to here, so it will fulfill the motion, right? So that's why before we have so-called advanced control system, linkages is one of the most reliable motion control, because this motion from C1 to C2 to C3, it will always very accurate, is from there. Until maybe recently, on these few years, especially now, people start to put into the application now to reduce this complexity on the design. Right? So a lot of people now move with sensors and actuator, right? Because you can easily put actuator to move this part, this C1 and D1 in this position as well. Right? When you have very good sensors and feedback system. Right? But linkages is still one of the most reliable. So because it won't go wrong. Right? Just like your bicycle, you cycle it normally, unless your chain break, there is a hardware breakdown. If not, nothing will go wrong. Okay? So we can move on to another example here. Okay, so three position synthesis with alternate moving pivot. So design a 4-bar linkage to move the link CD, right? So where is our CD? So we have CD here, C1 D1, C2 D2, and C3 D3. Use different moving pivots than the CD. Find the fixed pivot location. So what happened here is now we cannot put our joint on this CD location. Right? So maybe give you an idea is sometimes that is because maybe C and D will attach to another mechanism, right? But we want this point to link to another mechanism move at the desired movement position. So that's why we have to choose, right, the linkage to link to another point on the link, right? So this is the method. It will go slightly longer, right? Because now a bit more complicated now. So we draw the link CD in its three desired position again. Okay? Define new attachment point E1 and F1 that have the fixed relationship between the C1 and D1. Okay? So the easiest explanation, it means we will put the E1 and F1 in the same rigid body as C1 and D1. Okay? So instead of using C1 and D1, now we use E1 and F1, right, to define the three position of the link. So we'll do the same thing, then we construct a line between the E1 to E2, E2 to E3, yeah? Right? So maybe we are here, okay? So means that instead of C1, D1 here, now we find this, right? So what if you do it manually, right? So what happens is basically you can draw these 4 points on the paper or on the transparent paper. Then you move it to the second position here. Then you start to mark the point. So means that all these 4 dimension, all the dimension between these 4 points is same between the first position and the second position, as well as the third position here. So you can also mark this 4 point here, right? Because this CD is what we desired. But then once we define this, then we have to know what is the relative position to C1, D1. Then we can duplicate it here and duplicate it over here, right? So that's why from there, then we can use the E and F to construct our linkage. So the intersect of E1, E2 and the E2, E3 will give us the O2. So if we find the intersection from the F1, F2, and F2, F3, then it will give us the rotation, center of rotation for link 4, which is O4. Okay. Again, the bottom one is repeating the same thing, so we can check the Grashof condition. We can also check the toggle position. So if we need the driver, right, over here, so then we can build it according to the example 3.4 there. Okay, so that's why now we will not look at C1, D1. Right? After we mark down where is our E1, F1, E2, F2, E3, F3, so we will use this. Okay, so we will connect the E1 and E2, and then we draw the 90 degree. Okay, E2 to E3 here, we will get another line. So we will find out the intersection is here, which form our O2. So then the other one is F1 to F2. So we draw a line. F2 to F3, we draw another line. So we find out the intersection is here, which is O4. Okay, so now when we have the O2 and O4, then we can start to build our linkage. So that's why O2 to E1 will form my link 2. Okay, so the E1 to F1 is my link 3. Then F1 to O4 will be my link 4. Okay, so this is how we get our linkages. Right? So as I mentioned just now, in this case, maybe the C1 and D1 will be used to connect to other mechanisms. So you can keep on adding the linkages. Right? So that's why the other advantage of linkages is you can have one link, right? One drive to do multiple work as well, synchronous work. Right? So if I want to draw the linkage on another extreme position, so I can connect my O2 to E3. This is another extreme position. E3 to F3 link 3, and then F3 to O4 is the link 4. So then I can always build a drive system. So we have 2 points here. You can draw a line. Okay. Then you can put your driver here. Right, so I always call this, I put a motor here, for example. And then I can put you have to check this length. This length should be half of this. Right. Then this one, you can put the motor to do the rotation. And then this link will keep repeating its motion. Alright, in this way. So this one we call it driver. Okay. So this is what you can see in especially on the older machine. New machine, they try to reduce this because the other disadvantage of this linkage is it takes up space. It's a space issue. So our CAM system is also linked to, can be under these linkages. Right? In your car, you have a valve, so you can use the CAM profile to turn on and off your profile, which will sync to your crankshaft motion. Because your valve motion has to be synchronous to your piston movement. So all the valve until today, almost 99% of your car is using the CAM to control your valve in a synchronous method. But China, last few years, I heard that there's the China automotive companies actually using actuator and sensor. So instead of they have a mechanical connection between your crankshaft to the CAM, and that control your valve, So now they put a sensor on the crankshaft and then put the actuator on the valve, right? So to do it, right? But I don't think it's very reliable, so there is no further news on that. But surprisingly, recently I saw a video that mentioned that the Koenigsegg is using that method. I think their one maybe will be more reliable, so they can actually buy a very expensive system there because the car is not cheap. Okay? Any one of you know about Koenigsegg? The car brand Koenigsegg. Maybe I will find a video so I can show it to you. Right? Koenigsegg is one of the most expensive hypercar in the world. Right? I'm not sure anyone see it in Malaysia, Koenigsegg. Okay, so what is the time? 11:20. So as what I always like to do is I will touch a bit on the next topic before we go in the full one on the Wednesday. Oh, Koenigsegg Jesco is relatively older car already. Right. Because of the advancement on the automotive industry, especially on the hybrid. So I think if you are interested on this, you can watch a lot of videos. Right? They're trying to make more and more powerful car. Right? Mechanical engineers, we should tell people that it's not. The problem is not whether we can make a faster car. The problem is now whether the driver can drive the car faster, right? Just like the jet fighter, they can make it very fast, but then no human can sit inside, right? I think now the special trained pilot can only withstand up to 4 to 5G. The plane can fly even faster, can accelerate even faster, but we will touch a bit on the next one. So you will find out that the lecture 2, we have 3 lecture files there. So we have position analysis, velocity analysis, and acceleration analysis. So we will start with the position analysis, then continue with the velocity analysis, and then only the acceleration. Because the information of the position will be used for velocity, and then the information you find from velocity will be used on the acceleration, right? So it's a step by step, right? Okay, so we'll look at it on the position analysis. So we'll look at position analysis of linkages, vector loops, equation, 4-bar linkage, crank slider linkage, and then also the transmission angle and the total position. So the angle of link 3 and 4 can be measured with the protectors. Right? On one circuit has the angle theta 3 and theta 4, and the other one have theta 3 prime and theta 4 prime. Right? But I think when you look at this diagram, you might be confused because they are drawing everything in one diagram. But first, we try to identify the link first. So again, ground, we have O2 here to O4 here. This is considered link 1. Okay. Then the link between O2 to point A here. Okay. This is link 2. So I try to use different colors. So from A to B is link 3. And then for B to O4, but normally they call O4 to B, because the measurement is slightly different. The measurement is from O4 to B. This is link 4. Right? So this is a linkage. We have 4-bar linkage. Right? This one is called 4-bar linkage. Oh, sorry. Four-bar linkage. Okay. So before looking at the theta 3 prime and theta 4 prime, we look at what we have here first. Okay. So you can draw a reference point. That's why this is called the global coordinate system. Okay. This is a global coordinate system. We have X and Y here. Okay. X and Y here. So if we measure from this X position to the link 2, that gives us the theta 2. Right? So there is a theta 2. Right? So we call this global coordinate system. But then now come to another one, coordinate system. They call it LNCS, which is a local non-rotating coordinate system. Okay, so what it means here is this coordinate system, this origin at point A here, is moving. That's why you call it localized. This is localized. So means it will follow the point A. The origin for this LNCS will follow this point A. But then it's stated here non-rotating, means that the X will still always X as a horizontal. Right? Y is the vertical. Right? So that's why this axis will not rotate, but it will move according to point A. So that's why I call it a localized coordinate system. But this one, the global one, means it will always stay here. Right? This point will not move. Right? The O2 will not move. That's why here it's called global coordinate system. So the theta 3 is a bit tricky because it measures from this LNCS. Right? So you measure this theta 3. Okay. Have to be clear. So theta 2 measure from the x-axis here, you get the theta 2. But theta 3 is measured from this LNCS, so you get the theta 3. So again, theta 4 is measured from the another axis here. So you measure from here. Okay. So you get theta 4. Okay. You are not measuring from point B. That's why just now I said we will call this link 4 as O4B. So if reference is at the O4. Okay. So maybe to re-highlight again. So for link 2, your reference is here. Okay. Reference for link 2. Okay. So for link 3, your reference is here. Reference for link 3. But then for link 4, your reference point is here. Right? So you have to be clear on this. Right? So then from here you can, if you know the link length, right? So you can easily sketch this diagram. Right? So normally how we can do it. Right? So for example, you can have this. We can have O2 here. So if I know my link 2 is, for example, 3 cm here. So we draw a 3 cm. So we can draw a circle. Then you have to know where is your, then we have to know link 1 length. So if I know the L1, then I can set my O4 here. So if I know my link 4, for example, 5 cm here, then you can draw another point. So your connecting rod now can join at any point. For example, now this is where my link 4 is. Okay? This is where my link 2 is. So then I can connect this point to this point, which will form my link 3. Okay? When I have that two position, so I can also say now my link 2 is here. Maybe link 4 is there. So I can join it to form my link 3. Okay? And so on. Because this one I don't draw in scale. So if you draw in a proper scale, then your diagram will look nicer compared to mine. So this is how we can build. Right? That's why we as long as if we know the link and its angle theta 2, right? So we can make this, we can find the point A. Right? So that's why normally we will try to find the theta 2 and the length of the link 2, length of the link 4, and also theta 4. Then we can easily construct the whole diagram. Or else we know all the link with one angle, all the link length with one angle, so we can also construct the position of it. Right? Right, so this is how it looks like. So the other one is the second position. Just now the theta 3 prime and theta 4 prime. So I mean here, instead of now the B is at here. Okay. So what happens if I set my link 2 again is same as here with the theta 2. Now my link 4 go down with the theta 4 again. You have to measure from there, from the horizontal line. Then you connect this, you'll form a new angle here. So this is called theta 4 prime. Right? So where is your theta 3 prime? You have to measure again from here. Right? So that is theta 3 prime. Right? So again, if you look carefully, this point is the reference for link 2. This point is the reference for link 3. And then this point is the reference for link 4. Alright? So that's how you get your angles. Right? So this is a calculation you can use to calculate the angles. So the coordinate of point A, which is this one, right? You can use these two formulas as long as when we know the link length. The A here is the length for link 2. So then the cos theta 2 is this one. Right? So you can find the position. Where is this? And where is this? So this is A, X, A, Y. So the coordinates of point B are found using the equations of circle about A and O4. So now, if you see that, if you want to find this, so what you can do is, depending on how you want to do the, depending on where is the reference point you want to have. So if you look at here, this is to calculate the B, right? So what it means here is you will take this BX. This is BX. So then this one is BY. So you have to take BX minus the AX square, so you get this distance. Okay, so this is BX minus AX. And then you find this distance. This is BY minus AY. Right, so then we can get the B. Okay, using this. This is just a simple triangle. If I have A, B, and C here, I can always find C squared is A squared plus B squared. So this is 90 degrees. Okay. So if I want to find C, so you can also take this distance. This is D. This is D, yeah. Then you can minus the bx minus d. So you notice that it use bx minus d, yeah. The reason is because for link 4, O4 is your reference. Right? O4 is your, sorry, let me check. This is the C. Yeah. Right? So O4 is your distance. Yeah? So that's where you get bx minus d, and then the vertical one, this is same as the by. Okay. So this one will be bx minus d. Okay. So we get negative value. Right. In this case, we will get negative value because our reference is for the O4. Right. So this is a calculation. Let me see bx. So this is all the substitutions. So they are doing some solving. So you can try on your own. Because later when you start to do examples, then you will see how it is actually application of trigonometry, right? Not specially designed for mechanics or machine. It's just trigonometry. Right? So we can when you try to apply, then you will know what is all this equation derived from. So the other one is on theta 3. Yeah? As mentioned, theta 3, the reference is from the point A. Yeah? So if you go back, so you want to find theta 3, so you have to take this distance divided by this distance. Okay? So you can see this one is by minus ay. This distance, horizontal one, is bx minus ax. So I can find my tangent theta 3 is by minus ay divided by bx minus ax. Right? So you can always draw the diagram. So you know which one over which one is the angle. Let us double confirm. So this is what we have. So for theta 4, right, that is where you have to refer to this point. Right? So you will take, because it's measured from this, because now this is exceeding 90 degrees, so we will look at this side instead. Right? So we will take the y component divided by the x component. So that's why I said tangent theta 4 is equal to by divided by the horizontal component. We have bx minus d. Right? So this is how we get the theta 4. So remember, their reference is all different. Maybe I think I stop here. This one will continue on Wednesday. So later in the afternoon, 2 p.m., we will have our first practical class. So it should be a short one, maybe half an hour to 1 hour, where I will explain to you how to do the experiment 4 in your home. Right? So then you can prepare a simple report and submit to me. Right? So from this week onward, we will start our practical class. And on Wednesday also, I will release the assignment, right, for this mechanics of machine. Okay, so I think I stop here for today. So make sure everyone take your attendance by submitting the vote on this chat. My computer is slightly slow, 133. Okay. So yeah, I think that's all for today. If you have any questions? If not, see you, some of you, I will see you in the afternoon 2 p.m. and the rest I will see you on the Wednesday. Okay, thank you.